Hi everybody, welcome back to Chem 121. What do we have on the agenda today? Well, looks like we're talking a little bit about what's due and when in chat. Nothing so far. Nothing has been assigned yet. By the end of today, the quiz for Unit 1 will get assigned because we're going to finish Unit 1 today. And then we'll begin Unit 2, and next week we'll probably finish Unit 2 as well as talk about the lab, and that the lab assignment will be formally posted at that time. I usually do my lab discussion on the first day of week 2 or so don't worry about the lab just yet. We'll get to it. I'll make a little video this weekend at some point about, like, this is what you do for the lab and how you upload labs and do all of your answers and stuff like that. So we'll do that when we get to that point. All right, so I believe this is where we left off last time. We finished the first 2 chunks, so we're going to move on to the next chunk, which is taking matter and classifying it in various ways. I'm on the wrong screen. I'm clicking things and nothing is happening. All right, so on the screen, I have 2 different substances. I have water in a glass, and I have cake. Cake is delicious. Water is also refreshing. These are both good things to put in your body. But from a matter perspective, one of these contains only one type of substance, and we would be able to call it pure. The other is what we would consider to be a mixture of substances that we have put together. Now, if you know where I can get pure cake, let me know. But as far as I'm aware, that doesn't exist, because cake has all sorts of different things in it. It has sugar, it has cream, it has fruit, if you put fruit toppings on it. It has chocolate, it has milk, it has eggs, it has etc. Right? And all of those substances that I listed can be broken down into other categories themselves. So, like, for example, eggs are both protein and carbohydrates and fat. And that's probably true for almost all of these substances, too. Water, on the other hand, is just plain old refreshing H2O. That's the only thing that's in the container. So we're going to use this as a guide. We're going to define any substance that contains only one type of thing in it as a pure substance. And I'm just trying to find my highlighter here. There we go. We're going to define those substances in a little bit later on. Now, if your substance has multiple things in it, we're going to call it a mixture. That's easy enough. We just need to know what we are looking for and if there's one of those or a bunch of them. So I'm going to make a chart out of this. I'm going to show it on the screen here. This is going to be a little flow chart for categorizing and classifying matter. Does your matter contain one substance and only one substance? It's pure. Otherwise, it's a mixture. Then we are going to take pure substances and mixtures, and we're going to separate those into 2 categories themselves based on their appearance and other properties that we can observe. So let's look at the elements first. So on the screen, I have 2 different, not elements, I'm sorry, the pure substances. On the screen, I have 2 different substances that are considered pure. So a diamond can be pure because all it contains is carbon. Now, I don't expect you to know that diamonds are made of carbon. But if we assume that that statement is true and there's only carbon atoms in there, we could differentiate that from something that, say, table salt is pure. It's only table salt. There's only salt in the shaker. But that salt itself contains 2 atoms instead of 1. So we're going to assign some names here. So if there is only one element off of the periodic table, we're going to call it that, an element. If there are 2 types of elements or more, we're going to call the substance a compound. Now, at the beginning of yesterday, or not yesterday, on Monday's lecture, I gave you this link. Let me type it in the chat real quick. This was the link for p-table. And unfortunately, I have to copy and paste it into my browser. But when I capture that, that's big. Hold on. My real estate is at a premium here, so I don't really want to capture anything off the screen. There you go. You could see all of the different elements on the periodic table. So if you are looking at a substance and you recognize, oh, it only contains oxygen here, then it's an element. But if it contains oxygen and carbon, 2 elements, that would make it a compound. If it contains 3 elements, it's still a compound. If it contains any number of elements that is not 1, it is a compound. Now, an interesting thing about elements is that elements are the simplest block. They are elemental. You may have heard that word used in that way before. So you cannot break an element into simpler substances because it is already as simple as it gets. All there is in a diamond is carbon. You cannot turn that carbon into something simpler because carbon is the simplest basic block. It is an element off the periodic table. A compound can be broken down into simpler substances. For example, table salt, you could break apart all the sodiums and all the chlorines and put them all together individually into their sodium and chlorine piles. And with a little work, you could get elemental sodium and elemental chlorine back. I'm simplifying because there's some chemistry involved in that. But you can do this process to get elements out of a compound. All right, so you're going to have to discern, when given an object, is it a pure substance or a mixture? And if it is a pure substance, which of these statements best describes it? You'll have to describe it as either an element or a compound. And you can do that by looking at its chemical formula. Now, obviously, you don't really know that many chemical formulas, but you can look them up on the internet because it is an online class. So you could ask the internet, what is the chemical formula for sugar? And it will tell you C6H12O6. And then you would know, oh, sugar's a compound. That's totally fair. You're allowed to do that on a worksheet, and you can do that on a quiz or an exam. Generally speaking, in order to save you time, I will give you the formula for things like that on exam, so you don't have to go look them up. Because if I just asked you, is sugar an element or a compound, that's not really fair. But if I said, is sugar formula this an element or a compound, you should be able to mark compound. Let's talk about mixtures. On the screen, I have 2 mixtures. I have ketchup and I have Italian salad dressing down at the bottom here. And what I'm going to do is I'm going to distinguish these based on how similar different portions I take are. Just based on, I'm just going to circle them. So I'm going to take this portion right here, just the top edge. I'm going to take something from the bottom and then something over here. And then what I'm going to do is I'm going to compare all of the portions that I took. And if all of those portions are the same, as far as I can tell, that didn't work. Let's try that again. Erase. I gotta highlight that with a different color. There we go. If all of the portions that I have selected are indistinguishable from one another, then the solution that we are looking at is called a homogeneous mixture. Or the mixture we're looking at is a homogeneous mixture. But by extension, if I take different portions from my substance, and they aren't all the same at all. For example, up here, I can take... I lost the cursor. There it is. I could take this part and this part. This is mostly oil, but this is mostly the good stuff, right? Not that the oil isn't good in Italian seasoning or in Italian dressing, but all the herbs and the spices and the tasty bits, those all tend to sink to the bottom because they tend to be more solid, right? These portions can never be the same. I keep losing the cursor because it's so light. And if you have any two portions in your mixture that are different, in other words, all of them are not identical, we call that heterogeneous. So a mixture will be heterogeneous or homogeneous depending on its composition and its current state. Now, things like soda can change their state depending on what you do to it. For example, if you take a 2-liter bottle of soda and you immediately open it and then pour it into a bunch of different glasses. All of those glasses should be indistinguishable from one another. That would be homogeneous. But if you added food coloring to the soda, at the beginning, when the food coloring is mixing, it would be heterogeneous. There'd be more of the food coloring. We'll say it's blue for whatever reason. At the top than there would be at the bottom because it has to mix into the soda. Maybe you're doing this for like a kid's party or something, and you dye their soda with food coloring. It would be heterogeneous until that blue dispersed through the whole solution, and then it would be homogeneous again. So depending on what you do to your solutions or your mixtures, the label that you should assign it can change. With salad dressing, if you mix it really, 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 really well, it will be homogeneous for an instant, and then it starts to immediately try and separate out. With dissolving salt in water, if you pour the salt in there and it's settled at the bottom, that's heterogeneous. There's a section of the solution that has a bunch of salt in it, and there's a section that doesn't. That's the liquid part at the very top. But once you mix it really well, it will become homogeneous, okay? So these labels are not absolutes. A substance is not trapped in that state once you have given it its label. They are flexible, and they can change which label they take on based on their current state and or condition. Now down here, I have this little warning, like there's some leeway, so use your senses. The reason that I do that is because if you go down far enough, and again, it depends on the state, you can get into a gray area where it's hard to determine the difference between homogeneous and heterogeneous. For example, blood. Blood should be homogeneous because if it was heterogeneous going through your body, that would be a problem. But the blood in your veins and the blood in your arteries is different, right? So what's the deal? What do we classify it as? It gets more complicated if we look too deeply. So I'm going to give you questions that should have an obvious answer to them. There's our flowchart. You can use this flowchart to differentiate between types of substances. Start at the top, and you can only end up in one of the 4 bins at the bottom, okay? Think of this like a pachinko machine. You start here, and you cannot do this. That is not a thing that is possible. You can have something be a pure substance and a homogeneous mixture. It's going to fall into one of these bins, and just work your way down the table. Here are some visual examples from the very first textbook I ever taught out of. I actually went and scanned this, which is why the picture looks terrible. But it's a really good picture, so I decided to use it. Alright, so what I want you to do now is I'm going to put a bunch of these on the board. And in the chat, I want you to identify each substance as either a pure substance, a compound, a homogeneous mixture, or a heterogeneous mixture. Now, in the parentheses for each statement, I have given you some contextual clues as to what the substance is. The only substances in the intended answer are what are in parentheses, if parentheses are given. For example, nail polish remover, assume that nail polish remover is 100% acetone, and here's some information about acetone. Assume that poorly mixed gravel is these three things, and so on and so forth. For other stuff, you'll have to use your intuition. Do the best that you can, and be careful about this last one. We're going to have a discussion about it. Okay? So I'll give you 5 minutes to categorize these, and again, type your answers in the chat when you are done. See you in a bit. One or two more minutes. We'll go over the answers here. All right, let's go over the answers here. Now, if you've ever drank Red Bull and you've looked on the side of it, you've probably seen the list of ingredients. Anything with a list of ingredients is automatically a mixture. And Red Bull, when you pour it into, or if you pour it out into like 3 or 4 different glasses, all of them should be the same, right? Because you just opened it out of a container. So this should be homogeneous. There we go. Number 2, nail polish remover. If we assume that it is only acetone, acetone is the only thing that's in there, then it must be a compound because the formula contains more than one element. It's got C in it, it's got H in it, and it's got O in it. For number 3, poorly mixed gravel. Well, if you poorly mix something, you're automatically going to have a mixture. And of the substances that are in here, if we poorly mix them, we get whatever the heck that is that I just tried to write there. Which would be a heterogeneous mixture. This should be an H. There we go. How about nitrogen gas? Well, nitrogen is just an element by itself on the periodic table. So in nitrogen gas, if there's only nitrogen, it must be an element. Same thing down here with iron metal, because that's the only element that's present. So we'll just grab that one while we can. Pizza from your favorite pizza from your favorite pizza parlor. Is every bite of your pizza going to be the same? Well, no. The crust end is going to be different than the middle end that you eat to start, right? You eat the middle first, and then you eat towards the crust. That's how you eat pizza. If you eat the crust first, then you don't have anything to hold on to. Who would do that? Or if you're Canadian, like my family, like my mother would eat pizza with a knife and fork, which I find to be weird. But apparently it's a very Canadian thing. I mean, I take pride in my Canadian, my Canada-ness, I guess we'll say. But I eat my pizza with my hands. When soda has bubbles, those bubbles are probably going to be very, 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 very small. And so that should not influence the solution to be heterogeneous. Because that CO2 is dissolved equally throughout the soda. Now, initially, when it's like fizzing a lot and there's fizz at the top, then yeah. But that soda will not stay like that for very long. So the intent for these problems is what state will this be in, and which word best describes it for as it is most of the time. Now, nobody said the correct answer for where is the best pizza, unfortunately, and that was Zeke's Pizza. Zeke's Pizza is the best pizza. It is expensive, but I would highly recommend, like, if you want a good pizza, go to Zeke's Pizza. If I had to pick a favorite cheap pizza, I'd pick Mod Pizza. Mod Pizza's pretty good. And then finally, we got to talk about steel. What the heck is steel? A lot of people might think, oh, well, there must be some formula for steel, but there really isn't. Steel is a metal, and the way that we make steel gives us insight onto what it actually is. So to make steel, you take iron and a bunch of other elements, you throw it in a bin, and you heat the hell out of it until it's a liquid. This is how you make molten metal. You just heat it until it's really, 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 really hot. Then you let it mix really well, and you put it in a mold. Now, in the liquid state, even though it's super, super hot, it would be a mixture. In fact, it'd be a homogeneous mixture, right? But when you let it cool down, it becomes a solid, and yet it remains a homogeneous mixture. What's actually happening here is that steel, and there are others that are like this, is what's called an alloy. All alloys are homogeneous mixtures. Because to make an alloy, you are just combining some amount of stuff by mass with some other amount of stuff by mass, heating it up until it is a liquid, mixing it really well, and then allowing it to cool. And the result is different than what it was when it started. So, for example, bronze is copper and tin mixed together. You put mostly copper and a little bit of tin. And the result is something that is much more firm than either metal, which is cool. All right, so be mindful of that because alloys exist out there. And they're common enough, and alloys are not compounds because there's no formula for them. It's just mix this percentage with this percentage. All right, that's it for that section. Let me know if you have any questions. We're going to continue. Let's do some looking around at the periodic table. On the screen, I have some examples of elements. Some of these might look like you expect, but others might not. For example, calcium over there on the right. Calcium looks kind of strange in this picture, but we are showing you elemental calcium and not calcium as it shows up in things like milk or bone. Many substances look like metals when they are in their elemental form because they are metals. However, they behave very differently when you combine them with other things. They become colorful or they become brittle or stuff like that. We're going to differentiate between that as we continue through our exploration of chemistry. Now, what exactly is an element? An element is any substance that is one of the things on the periodic table. Now, we haven't discussed what elements are made of yet. We're going to talk about atoms and molecules in the next section. And then in a... what chapter do we do that in? I'm not sure when we do protons and neutrons and electrons, actually. I think it's chapter 3. But we're going to talk about what makes up an atom specifically and how we identify atoms later on in the class. So for now, just be aware that these things exist. That there are 118 of them on the periodic table. All right. On the periodic table on the screen, you could see that there are some blanks in here. Since I have written these slides, these blanks have been filled in with elements that have names. And in fact, the ones 110 through 114 have also been given names instead of UUN. This slide is just old. Now, a lot of this is actually obsolete for this class, so you can use whatever periodic table you want to, so you can ignore this. And in fact, you can ignore this one too. Because if you have a periodic table with names on it, then you don't need to learn the first 20 elements. Although, the first 20 elements are the most common elements, I should say. So it's worth knowing them. But the things I would absolutely advise you to do are to look for any elements that have symbols that don't match up with what their names are. For instance, if you're looking for potassium and you look over here, that's phosphorus that I've highlighted in yellow. Potassium is actually K. That's this one right here. And the reason for that is because the name for potassium in Latin is called kalium. Some of the elements have Latin names. For example, sodium is Na. That's natrium. That is Latin for sodium, I guess. That just happens for elements that were discovered and known in antiquity. So, not all elements are going to have names that match up with what we call them today. And in fact, some of the names have weird spellings where letters are just omitted. For example, this is the most common weird one. For chlorine, the symbol is Cl. There's an H in chlorine, but the H is silent, and it also doesn't even appear in the symbol. So just be mindful of that. You cannot always intuit the symbol from the name. All right. All symbols for any element that we use are going to have one or two letters. And most of them make sense, but again, there are some weird ones. And they come from different languages because those people found them first. They were well known. Those names had been used throughout history. Why change them? All right, so for this exercise, I'm going to give you like 2 or 3 minutes to pull up ptable.com. And what I want you to do is just get the idea of where these elements are on the periodic table. So pull up the periodic table website, look around for a bit, and then we'll move on to the next section. And once we finish that, we'll take our break. So see you in a bit. All right, please finish up. I'll give you another minute to look over it. I did not mean to hit that button. All right. So, I'm not going to write down all of the element names. Or I'm sorry, I'm not going to look these up on the periodic table, but I will write the symbols next to these for you. In case you want to look them up on your own. And I've picked some that are pretty common ones to swap with another. Tin and titanium is a really common one. Phosphorus and potassium is another common one. And then anything with a C in it, you have to be careful. So there's calcium, chlorine, cobalt, chromium, copper, carbon, californium. Like there's just tons of them that start with the letter C. So just be very careful about those elements. And as you become more familiar with the periodic table, it gets much easier to navigate. Like I could probably fill out a blank periodic table like without a second thought. I just go straight through 1 through 118. But I've been doing this for 15 years. You guys have been doing this for about what, 15 minutes, I guess. So, my expectations for you are much different. So, always have P table handy, have it bookmarked. You can put a link to it in the Discord and just have it like pinned there or something like that. As long as you know where it is so you can access it. All right, let's talk about one more thing before we take our 10-minute break. Let's talk about what elements are at the smallest possible level, because we've been talking about them in this nebulous sort of way. Like, oh, what is an element? Okay, well, I have carbon. Well, what is carbon? It's a collection of carbon. But if I get down to, like, the smallest pieces, what makes up carbon, we're going to get to this discussion, which is the atomic nature of matter. So I'm going to give you copper for this example. Here's a copper sheet. And your first task is to cut it in half. Well, you can do that pretty easily. Boop, there you go. Then your next task is to cut it in half again, and then do that again and again and again and again and again. Over and over and over and over and over and over and over. At some point, you will get down to the smallest piece that you can possibly get to, and still have it be copper. And that is called an atom. Now, if you try to cut the copper in half itself, I'm sorry, the copper atom in half, then the result that you get is not copper anymore. What you're actually doing is nuclear chemistry. You're going to break the copper into whatever its constituent pieces are in roughly half. Now, if you've taken any sort of chemistry class before, you've probably heard of protons and neutrons and electrons. And if you cut this atom in half, you're going to get half as many protons in each half as possible, and you'll get something totally different, as you will learn later. Now, since we're doing this over and over and over again, but it's still copper every time, this process must be a physical process, as we discussed on whatever the first class day was. I haven't learned the schedule yet. Monday. It's written on my streaming software right here. Now, where do all of these atoms come from? Like, where do these elements come from? What we're going to learn is that the atoms that are present around us are made of smaller particles themselves. But when we form those particles, they become discrete units called atoms that have various properties. If I have a pure substance and it contains a specific element, such as, say, oxygen, then everything in that sample of oxygen is identical. All the atoms of oxygen are all identical to each other. All atoms of copper are identical to each other. All atoms of carbon are identical to each other. But carbon and oxygen themselves are unique. Carbon does not behave like oxygen, and it does not contain the same stuff in it as oxygen. Now, on the screen here, I have a picture that shows the elemental composition of the sun. And the sun is kind of just a blueprint for the universe, because the universe was as it was, and then the stuff that was in it coalesced into stars to make the sun. So this is our good approximation of what's in the universe. The universe is mostly hydrogen. It's got a fair amount of helium, and then this teeny tiny sliver is absolutely everything else. Now, where did all of this stuff come from? Unfortunately, I cannot play this video because I guarantee that my video will get copyright struck. But I will play like the first few seconds of it really quickly here. How did this happen? And so you can hear that was the question that was being asked there, because this is the video. Oops, that's the wrong window. That's not what I want. Hold on.
A long time ago, actually never, and
sorry, hold on. I'm playing the video in the background, but I don't actually want to play it. I just want to put this on the screen so that you can see it. There we go. You may have seen this video before. This is called The History of the World, I guess. And it is very, very popular. It has been viewed 116 million times in the last 4 years. It is a 20-minute summary of all of history as we know it, from the Big Bang all the way up until today. And so the first, like, 4 or 5 minutes is physics and chemistry, which is actually relevant to this. And then past that, it becomes biology and then history. And I will link this video for you in the chat if you want to watch part of it during the break. I really only care... Oops, I hit copy a second time. That was silly. I only really care about the first few minutes, about like where stuff becomes stars and then the stars explode, and that's how you get the elements. So if you wanted to know where all of these elements come from, it's from stars exploding, which is cool and all. And so I'm going to leave that video for you to watch on your own time, because if I play any more, I'm sure that it will get scrubbed from the video, and they may mute that section for students later on, and I don't want that. So I will provide that link for you. It's a really good video. It's really entertaining. The guy who does all of that work does all his own music. He does all his own sing-songy stuff. The graphics are intentionally crappy because that's the gimmick. It's supposed to look fun. And it's a really good video. All right, so now that we know what atoms are, at least fundamentally, they're just individual units that we have applied labels to: copper, oxygen, or I almost said orange for some reason. Copper, oxygen, fluorine, neon, manganese, beryllium, hydrogen, etc. What happens if we stick a bunch of atoms together? So if I draw a picture, so here's my oxygen atom like this, just floating around. And here's some hydrogens, and I'm going to just have them float around too. What would happen if I were to bond them together through some sort of force? The result that we get when we bond atoms together is called a molecule. And so we're going to use this term quite a bit in this class. So if we have atoms that are stuck together, and we need at least 2 or more, the result is called a molecule. So water, for instance, is a molecule. It is oxygen and 2 hydrogens, and they all travel together as a group. I mean, this is Seattle, so you've probably heard the term polycule. And polycule means like a number of people who are in a relationship with each other, and they're basically stuck, in quotes, together because they have a relationship. They have a bond. And so the word molecule is where the word polycule comes from. Now, these atoms are very difficult to separate apart. So turning water into something else requires a chemical reaction. Water is very stable on its own, and it tends to not react unless you expose it to very specific conditions and chemicals. Now, what's the difference between the molecule and the atom? Each of these individual things within the molecule, so this is an atom, and this is an atom, and so is this one over here. Together, they make the molecule. So that's the difference between these. Lots of matter out there is molecular. We're going to be seeing molecules all over the place as we discuss chemistry further. All right, let me clear my ink here. On the screen are some examples of molecules. Water, we just drew. Oxygen is another molecule that's common. When you take a deep breath, about 20% of what you're breathing in is oxygen. And all of those oxygen molecules are two oxygen atoms bonded together. They don't travel alone, they travel in pairs. Now, why do we have H2O instead of, like, say, just H2 or H2O2 or HO2 or whatever? We're going to talk about that when we get to the chapters on bonding in units 4 and 5. So, for now, we'll just accept that molecules exist. Just like we categorize matter, we're going to categorize molecules too. The first category that we're going to use is just referring to the number of atoms. So I've drawn some pictures here to represent some atoms. Each sphere is an atom. So here's an atom. Here are 2 atoms. And then this one has 3 atoms. We're going to base this based off of how many spheres are present or how many total atoms are in our formula, because we're going to eventually move to formulas. So if something is only 1 atom, we would call it monatomic. Mono meaning 1. Something with 2 atoms would be diatomic, and something with 3 atoms would be triatomic. If you have more than 3 atoms, you could do tetraatomic or pentatomic or whatever, but the convention is we just, at that point, we start calling it polyatomic. So this is a label you can apply to any picture or any chemical formula that is written out. The other label that we can apply is the number of types of atoms that are there. So you can see in the middle picture, I only have 1 color. So both of those atoms are the same element. But on the picture on the right, I have 2 colors, so there must be 2 different elements present. And we can treat that in the same way. If there's only 1 type of atom, we're going to say homoatomic. And if there are 2 or more types of atoms, we'll say heteroatomic. So all of our molecules can have 1 of each of these categories of labels. You're going to give it either homo or heteroatomic, based on what types of elements are there. And you're going to give it a monatomic, diatomic, triatomic, etc., based on how many total atoms there are. All right, so let's do that. On this screen, these lines that are shown here, these are just separators, okay? So these are 6 different problems. I'll even number them. 1, 2, 3, 4, 5, 6. And what I want you to do is for each of these problems, 1 through 6, I want you to give it one of the labels from each category. Homoatomic or heteroatomic, and monoatomic or diatomic or triatomic or polyatomic, based on the picture that you see. Now, on the bottom set, you have formulas. You could represent the formulas as pictures, but that's tedious, and we want to write stuff out in the symbolic domain if we can, because it's way easier to write C6H6 than to draw 12 circles, however these atoms are bonded to each other. Okay? So treat that as if it were a picture and interpret it in the same way. How many total atoms gives you the mono, di, tri, poly label. And then how many types of atoms are present will give you the homo or hetero. Okay? I'll give you a few minutes to do that. Type your answers in the chat for each problem when you're done. and then we'll go over the answers and we'll take our break. See you in a bit. All right. 1 or 2 more minutes. We'll go over the answers together. All right, let's go over the answers here. All right, so for this first one, I have 1, 2, 3 atoms, so that makes this triatomic. And of those 3, they're all red, so that means they're all the same element. So this would be homoatomic. There you go. 1, 2, 3, 4, 5. 5 is polyatomic. And there are 2 different colors, red and blue, so this would be heteroatomic. This third one, all by itself, poor guy, monatomic. And if you have something that's monatomic, it cannot be anything other than homoatomic. All right, going down to the bottom here, I have 6 plus 6 is 12 different atoms, so this would be polyatomic. But there are 2 different types of atoms, so this would be heteroatomic. For number 5, there's only one type of element, but there are 2 of these atoms. So this would be diatomic. And I don't know why I wrote M instead of H there. Homoatomic. And then finally, 1 atom plus 2 atoms is 3, so this is triatomic and heteroatomic. All right, on the screen at the very bottom is the homework for this section that we just discussed. So I recommend doing those problems for practice. Do as many as it takes until you become comfortable with all the content that we've covered here. I believe that is the end of chapter 1. Let me just double check real quick. Oh, there's like 2 slides, but we're going to do those 2 slides when we get back from the break. So let me put this on the screen here. I didn't clear the timer, did I? Yeah, that's from the last class, so boop. There we go. All right, so I'll see you in 10 minutes. We're going to take a 10-minute break, so we'll start the clock, and we'll be back in a bit. Oh, so close. That's okay. All right, welcome back. We do have like one or two more slides left to cover before we finish off the chapter. So let's talk about chemical formulas just a little bit, because I was showing some of them on the previous slide. What is a chemical formula? A chemical formula is a specific notation that we use that represents how many atoms and of what types of atoms are present in a specific compound. So for instance, if I had something that had one copper atom and two chlorines in it, I would write it like this: CuCl2. You'll notice that if there's only... Oops, I'm sorry, I dropped my pen on the spacebar. You'll notice that if there's only one atom, I don't put a 1 there. I just write the atom as is. And that my numbers are subscripts after each specific element. Now, I could also use parentheses here. So, for instance, if I had, like, say... Oh, that's the wrong pen. So, if I had copper nitrate, for example, which might have this as its formula, then this too applies to all of the stuff in the parentheses. So, you may see some parentheses. In fact, you will in the next problem. So just be aware of that. All right, so for example, let's suppose I'm looking at ammonia. Ammonia is 1 nitrogen and 3 hydrogens. If I wanted to write its formula, well, I just do, okay, there's 1 nitrogen. Boop, there you go. There's 3 hydrogens. And you're all set. And again, don't put the 1 in there. Never put 1s in chemical formulas. If I want to do this for phosphorus pentoxide, this should be diphosphorus pentoxide, but that's okay. 2 phosphorus, I'd write this. 5 oxygen, I would write this. Now, how do you know which element to put first? For a while, we're not really going to know how to do that until we get to, I think it's unit, I want to say it's 7 is when we start discussing that. The actual way that you determine which element goes first is which one's more positive. We put the positive element first. Usually that's the element that's further to the left on the periodic table. We're going to discuss why that is in the coming weeks. But for now, when I give you a formula, just write the elements in the order that you are given them, because I'm not going to mislead you and put the oxygen first and expect that you know to flip that. All right. So just for practice, so that you get familiar with looking at these formulas, what I want you to do is I want you to count the number of each element in each molecule as shown. So in coding, that's really straightforward. Okay, yeah, there's 18 carbons and so on and so forth. But as we start putting in parentheses and start writing formulas in weirder ways, it gets a little more complicated. So in the chat, for each substance, type out how many of each atom there are, and then we'll sum them all together. Be particularly careful with parentheses and places where atoms show up more than once. And I'll show you for each of these examples why these are written in this way when we go over the answers. So I'll give you 5 minutes to do that. See you in a bit. 1 or 2 more minutes. We'll go over the answers. We may have to wait a little bit longer because they're renovating an apartment next door, and I think they're moving something heavy down the stairs, and my entire apartment is just shaking. So, I don't know if you can hear the thump, thump in the background, but give me just a minute, and once that's done, we'll start again. I mean, complain and ye shall receive, right? So I guess it went away. So let's go ahead and go over the answers here. So for this first one, I gotta get a different color. This first one's pretty straightforward. Since all we're doing is reporting just the numbers that are right there and there and there and there. Oops, I gotta hit show on that real quick. There we go. Down here, though, it gets a little bit more complicated. So calcium is definitely 10, so we can report that. But for phosphorus and oxygen and hydrogen, we have to worry about these parentheses. So the 6 applies to both of these things as a multiplier. So you could think of these as 6 clusters of PO4. So there would be 6 phosphorus. And then for oxygen, there's 24 of them inside that cluster, but there's also 2 right here. I can't write the number 2, apparently. Ah, I didn't select the pen. There we go. And then for hydrogen, same thing. Now, why do we do that? It's because those ions that are in parentheses, these are called polyatomic ions, particularly PO4 is phosphate, OH is hydroxide. Those are really common, and they stick together in those forms. And we just encounter them like that. So we write them as groups, grouped in parentheses, because they don't split apart on their own. I'm just checking something. Oh, damn it! I talked over it. I'm just checking to see if the thumping is appearing on my if it's spiking on my audio here. This next one's also kind of weird, but you could just count up the things. So here's 2 carbons. There's 4 hydrogens, so 1 and then these 3 over here. And then for the oxygens, there's 2 of them like that. Now, why is this written in this way? So I'm actually going to show you that on the screen here. Where did my PowerPoint go? There it is. Now, in organic chemistry, which you'll take in 131 if you want to take that course, sometimes molecules are written in a linear fashion. And so when I have this molecule, there we go. That was pretty bad. We sometimes write it as it would appear when it's bonded, left to right. So this molecule, vinegar or acetic acid, actually looks like this when we draw its structure. And so you could see, here's the CH3, Here's the CO, and here's the OH. Now, obviously, you would not know that at this point in the class, but later on, when we start drawing structures of molecules, you'll see that sometimes it becomes easier to just represent what they actually look like by writing the formula out a little bit more complexly, as opposed to writing C2H4O2, which doesn't tell you anything about the structure. So there are many ways to write formulas in chemistry. For this last one down here, so obviously there's only one platinum, and there's obviously 2 chlorines. But for the nitrogen and the hydrogen, I got to multiply this 2 through. So there's 2 nitrogens and 6 hydrogens. There you go. All right, so that's chapter 1. If you have any questions, let me know. Oops, I have audio at the end of this to celebrate, so hooray! That's it for chapter 1. It does get harder. We're going to jump right into the harder stuff with math in Unit 2. So the screen's going to go black for just a second because I have to unload the slides that are there and load the new slides. So let me go like this. Boop, there we go. It should appear. There it is. All right. One of these sections is actually not covered in this textbook. Oops, I meant to draw there, but I instead clicked. We're not actually going to do the section on heat. It's included just because these are... when we had an earlier edition of the textbook, it had a chapter on heat and calorimetry. The newer edition doesn't for some reason. It was omitted. So I just left the slides in there in case it came back for some reason. It hasn't. So we're not going to do the last section of this chapter. We are going to do the rest of it. The emphasis of chapter 2 is measurement and numbers. In many points in allied health, you are going to need to record numbers in some manner. For example, if you do a blood draw and you analyze the contents of a patient's blood, you'll want to know what the concentration of sugar is in their blood, for example, to determine if they're having a diabetic episode, for instance, like if their blood sugar is way too high, or if it's way too low because they have taken too much insulin, or something like that. Or maybe you need to measure the correct amount of medication to administer to a puppy. And if you overdose the puppy, they could be in severe danger. So you want to make sure that you measure the correct volume of the medicine before you give the injection or the pill or whatever to the pet. We're going to deal with all of that in this unit, and we're going to show a specific method that gives you calculations that are not only reliable, but also reproducible based on the numbers that you see there. And that does involve a little bit of relearning how to do basic math, which surprises a lot of students. And that's going to be these sections right here. A lot of people get to this part of the course and they're like, oh my goodness, I thought I knew everything about addition. You just plug it in the calculator. You got to do a little more work than that. And we're going to talk about that in this unit. So, first thing we want to do, let's talk about how we do measurements. Like, what does it mean to make a measurement? Whenever you need a number associated with some sort of quantity, you're going to need 2 parts. So to answer these questions, each of these would have an answer that has 2 parts to it. Something would be a number, and then something would be something to classify that number. If I just said 4, I have 4 blue powder. That doesn't make much sense. But if I say 4 grams, that lets you visualize, oh, okay, I know how much that is. That would be different than 4 pounds, which would be much, much more than 4 grams, right? So we're going to need both of those parts to answer questions like this. So for all measurements, we're going to have 2 parts to it. The first part is the measurement itself. The measurement is a number that we generate based on some sort of tool or our ability to measure ourselves, which it turns out people are very poor at measuring. If I said draw a line that is 10 centimeters long, you would not get very close without a tool, because we're just not very good at estimating that. You could get probably within 1 centimeter if you've been working with rulers for a long time, but you certainly could not get within 0.01 centimeters. If you did, that would just be chance. Now, along with the measurement, we need a unit. If you don't have a unit, the value becomes meaningless in science. For example, this sign that you might see on the side of the highway means nothing to a scientist. Unfortunately, that defense does not hold up in court. I've tried to ask a lawyer about that, and he advised that I probably shouldn't bring that up. 65 what, officer? Oh, I was going 65 feet per second. The units weren't shown, so I didn't know. Yeah, don't try that, right? So colloquially, we know that the units for this are in miles per hour. But we need to have that written there in science to make sure that it is absolutely clear. Now, a situation can arise when you go to Canada and they measure all their speed limits in kilometers an hour, but the numbers get way bigger. For example, if you're driving 100 down the highway in Canada, but you're going 100 at the wrong units, you're going to get pulled over because the speed limit's not 100 miles an hour, it's 100 kilometers an hour, which is roughly 60-ish miles an hour. So for all these units, we need to have the unit explained on the end of our measurement, or else the measurement itself is invalid. Okay, so for anything that you write down with a number, you need to include both the number and the unit. Don't forget the units, because otherwise I mark it wrong. Now, that explanation of me marking it wrong is for the in-person version of this course, where you would be writing stuff on a paper and you'd turn it in, and I might ask you, like, how many centimeters are in 43 miles? And you do the calculation, and then you'd report the answer and give it to me. And if you didn't write centimeters at the end and just gave me a number, I'd have to mark it wrong and deduct some points for it, because you need to have that centimeters on there to tell me. On Canvas, and this is important, Canvas won't allow you to put units in your answers because the fields that you are typing in answers for only accept numbers. If the answer is 15.5 centimeters and you type in 15.5 space cm, Canvas goes, enter a number in this field, because it doesn't know what you're typing. So in Canvas, you cannot enter the units, and I will tell you that. Enter just the number, or enter just the value. On a lab report, and we'll go over to this screen to talk about that real quick. On a lab document, whether you need to include units or not depends on the context of the problem. So you might have like a table, for example. And for instance, maybe I'm asking you to report the mass of the sample that was used in a video, and you have to write it down in the table. When you write the number, you'll also need to put the unit in there, or else the answer would be marked wrong. So you do need the unit somewhere. Now, another way to do this is to put the units over here, and then you could say, what is the mass in grams for trial 1? Okay, it's 42.505. I have already indicated the units in the table, so you don't have to, and so this would be okay. You need to have the units either here or here. If you have it in both places, that's fine. Being redundant in this case is okay. But if you didn't have the unit in any spot at all and you just entered a number, it would be marked as partially incorrect. Okay? So be mindful of that. Make sure you are aware of the context of what it is that you are filling out. Canvas will not allow units, so ignore units on Canvas. Just type in the number, because that's all I can do. But on the lab documents, if there's anything that asks for units, make sure you type in the units after it. Unless it's already in the table for you. Then you don't have to. You could just print the number. All right. So let's examine some ways that we can measure things. In terms of like specific dimensions and then the units that we're going to use. So the first system that we're going to use for measuring is stupid. So this is the imperial system. And the reason that it's stupid is because the numbers that are used in this system are all over the place and are awful. I don't know who decided that there were 12 inches in a foot and not, say, 10, but that's dumb. So now I had to remember 12 instead of a round number that is easy. 3 feet in a yard. I don't know. I'm not even going to try to figure out why they picked that number. And in fact, if I go to the internet, let me put. I'm putting the stylus in my teeth here. Let me find. I'm trying to find a chart here for imperial conversions. Yeah, there's the specific one that I'm thinking of. Images. Where is it? Here we go. That's really tiny. Can I get it bigger, please? Where is the picture? It's on Wikipedia. Oh, there it is, right there. Here we go. Let me show you all of the different wonderful imperial units that we can have. Here they are. I can't really make it bigger, unfortunately, but what I can do is I can do this and then make this bigger. This is all just for length. And these are the short lengths, so I can go like this and make this longer. There are the longer lengths. And I guess it keeps going over here. Yeah, there we go. Oh, those are metric on the side there. How would you like to calculate how many cables there are in a Gunther's chain? Because you could totally do that. It's just really, 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 really stupid, right? Like, nobody in their right mind should have to memorize all of these numbers. That there are 6,080 feet in a nautical mile, and that's 3 leagues. Like, who decided all this? And the answer is morons did. Morons decided this. This is dumb. Everything is dumb. I hate it. I hate it so much. So that's why we're going to use metric. Metric is so much easier because everything is just powers of 10. And so we can get a whole range of lengths by just remembering a prefix and then a number associated with it. So for instance, milli right here is 10 to the minus 3. Kilo is 10 to the positive 3, or 1,000. Centi is 10 to the minus 2. And then we don't have to just worry about doing this for length. We can apply centi to whatever. We could do centiliter, centisecond, centimeter. Like, you just apply it to whatever it is that you want. So the metric system is super, super useful. So my task for you is to learn and have the numbers for the metric system in memory so that you don't have to look this up every time you do it, because we'll use it so often that it is something that is worth committing to memory. On one of these slides, I have the metric chart. In your textbook, table 2.2 has a bunch of conversions between imperial and metric. You can also look these conversions up on Google, but don't memorize them. Just look them up every time you need to use them. So like if you're doing feet to meters, for example, look that up. It's written on a chart somewhere. Let me find I'm going to skip this really quickly. There we go. That's what I'm looking for. Here are the metric prefixes that are commonly used in allied health. You don't really go past mega. So like giga and tera, those are prefixes that are typically used for things like hard drive size or number of computing cycles per second. But mega, kilo, those are common enough. Deci, centi, milli, micro, those are also common enough for things like dosing. How many milliliters or how many micrograms per milliliter. Blood sugar is measured in milligrams per deciliter. Nano and pico are reserved for atomic distances and wavelengths of light and stuff like that. And we're not really going to cover those topics in this class, but they're there. So the ones in red, you should definitely try and commit to memory because you're going to use them so often. All right, I'm going to leave that on the screen for just a second in case you want to write that down or something. I don't know. All right, I'm going to go back to the slides that I skipped because I want to talk about the units that we're going to be using and that we're going to apply these prefixes to. So the first one's length. We've already talked about length. Length is the distance between any 2 points that you choose. We're going to measure length exclusively in meters of some sort. So that would be either just regular meters by themselves, or kilometers, or centimeters, or micrometers, or whatever. We're going to apply a prefix to modify it as we see fit. Volume is the three-dimensional space that an object contains. The unit that we're going to use for volume is liters. Now, a liter is a specific volume. It is half of the size of a 2-liter bottle. Sometimes we want more liquid than that. Sometimes we want less liquid than that. We modify it with a prefix appropriately. And we do that for all of these. We're going to measure mass in grams because in a chemistry class, we're oftentimes operating in grams. A more common unit that is used is the kilogram because weighing a person in grams gives a number that is insulting. Yeah, Doc, how much do I weigh? Well, it says here you weigh 110,000 grams. Yeah, I don't need to hear that. All right, just say 110 kilograms. Soften the blow, right? All right. Time is the interval between any two events. We're going to measure time in seconds. Sometimes we need milliseconds. Sometimes we need longer. The weird thing about seconds is that we have other units that are just so common. We don't really measure in kiloseconds. Like 1,000-second increments is kind of weird. Milliseconds is totally useful. But if you get 60-second increments, then we start calling them minutes and stuff like that. And that's common enough that we do that. The last unit is actually new, and you may not have heard of this before. So quantity is measured in a amount called the mole. So a mole is a collection of things, kind of like how a dozen is 12 things. A mole is this many things. So 1 mole of things is this many things. 6.022 times 10 to the 23. That is the most ginormous number you could even ever possibly conceive. And the reason that it's so big is because atoms are so small. We're going to talk about the mole again in chapter 6, so just remember it exists. We're not going to use it today or anytime soon. We're going to use that probably after exam number 1. Now again, we can modify these these units, meters, grams, liters, seconds, and moles, by using a prefix. So we know how long a second is. We could turn the desired quantity into a millisecond by dividing by 1,000 or multiplying by 10 to the minus 3. So I'm going to show an example of how we do that. And then we're going to save the rest of that for next time because we're going to run out of time before we start diving into these calculations here. Oops. Oh, no, I guess we're not going to do that at all. Where does that... Oh, that happens way later. Okay. Well, then that's it. That's all we're going to do today. Okay. So I'm going to leave this on the screen here. I'm not going to start the next section with 5 minutes or 5 to 10 minutes left in the class. So we'll call it a week for here. But one thing that is going to happen is that because we have finished Unit 1, or Chapter 1 in this class, I'm going to put the quiz for Chapter 1 on Canvas. And so that's going to be given a due date 1 week from today. The way that quizzes will work in this class is that whenever we finish a unit, the day that the unit we is finished, I go to Canvas and I say, okay, the quiz is now available, and you get 1 week to do it. So we'll even add it to the announcement here. So quiz number 1 will be due 1 week from today, and so that will be Wednesday, April 14th. Okay. Now, any due date that I show on these announcements down at the bottom here is a soft deadline. So remember how deadlines work. That's the due date, but if you miss that deadline, you still have one extra period, 1 day to turn it in. So the closing day will actually be Thursday. Okay. After Thursday the 15th, if you try and turn it in beyond that, the quiz will just disappear and you won't be able to do it. Okay. So you'll see that on there tonight. I'm going to go and put that in there after lecture. I'm going to go get some food because I'm hungry. And then when I sit down again, I will get to work on that. But expect that on Canvas. There will be an announcement that is sent out. And then after that, you can just complete the quiz whenever you want to. Remember that it's open resource. You get to do it. You get to take the quiz twice. The only thing you cannot do is ask me any questions. So I cannot answer any questions specifically related to the quiz. But other than that, that's all I got. So thanks for coming out to the lecture. I hope that you enjoyed it. I will see everybody next week on Monday for Chapter 2. And we'll talk about the lab at that time. Have a wonderful weekend, and I'll see you next week.